So we've made it to our last section in the course, Chapter 12.4, Conic sections. Coming a long way, baby. Conic sections are best visualized as the Greeks did over 2,000 years ago by slicing a double cone with a plane, and you can see this in many different formats below. 3 of the 7 different sets of points that arise in this way are ellipses, parabolas, and hyperbolas. These curves have practical applications and broad theoretical importance. For example, celestial bodies like planets travel in orbits that are modeled by ellipses and hyperbolas. Mirrors for telescopes are designed using the properties of conic sections, and architectural structures such as domes and arches are sometimes based on these curves. So you can see how in the diagrams below, depending upon we slice through these conic sections, we get different shapes and possibly even simply a plane or lines or systems of linear equations. A parabola is the set of points in a plane that are equidistant from a fixed point F, called the focus, and a fixed line called the directrix. In the 4 standard definitions, a parabola may open upward, downward, to the right, or to the left. We're going to derive the equation of the parabola that opens upward. Suppose the focus F is on the y-axis at 0, p, and the directrix is the horizontal line y equals negative p, where p is greater than 0. The parabola is the set of points that satisfy the defining property that PF, the distance from the focus to the parabola, is the same as PL, the distance from a point on the parabola to the directrix. So PF has to equal PL, the distances here that you can see in the diagram to the right. Where LX opposite of P, or negative P, is the point on the directrix closest to P. Consider an arbitrary point P, X, Y that satisfies this condition. Applying the distance formula, we have the square root of x squared plus y minus p squared. Notice this is the distance PF equals y plus p, and notice this is the distance PL. Okay. Squaring both sides of this equation and simplifying gives the equation x squared equals 4py. This is the equation of a parabola that is symmetric about the y-axis and opens upward. The vertex of the parabola is the point closest to the directrix. In this case, it's the origin, 0, 0, which satisfies the distance, the absolute value of PF, which is the distance of that line segment, equals the absolute distance of PL, which equals P. The equations of the other 3 standard parabolas are derived in a similar way. So let's look at the equations of 4 standard parabolas. Let P be a real number. The parabola with a focus at 0p and directrix y equals negative p is symmetric about the y-axis and has the equation as we saw before, x squared equals 4py. If p is greater than 0, then the parabola opens upward. That's the one on the left here in the green. And if p is less than 0, then the parabola opens downward. Okay. The parabola with focus at P0 and the directrix x equals negative p, you can see that point here. The directrix is a vertical line now, is symmetric about the x-axis and has the equation y squared equals 4px. These are the equations or the graphs you see in the orange. If p is greater than 0, then the parabola opens to the right, and if P is less than 0, then the parabola opens to the left. Each of these parabolas has a vertex at the origin. So let's look at our first example, graphing parabolas. Find the focus and directrix of the parabola y squared equals negative 12x. Well, we can see that this is a parabola that's either going to open to the left or through the right. So at least that's one clue that we have up front. We also have the general form of the equation, y squared equals 4px. And so we can see 4p is going to be equal to negative 12, or p is going to be equal to negative 3. Okay? Remember, if p is less than 0, then the equation is going to open to the right. And remember that our focus is at P0, so it's at negative 30, and the directrix is at x equals P, which is, or x equals the opposite of P, which is x equals 3. And so here is our diagram for this, with the focus of negative 30 and directrix x equals 3. Okay? So this little summary here, but of course you need to know which is positive and which is negative. And so to the left and up are positive, and to the right and down are negative values of P. So now let's look at a different take on a similar problem. How do we find the equation of the parabola? Find the equation of the parabola with vertex 0, 0 that opens downward and passes through the point 2, negative 3. Well, we know that a parabola that opens downward is equal to x squared equals 4py, and p is going to be less than 0. If we use this general form of the equation, x squared equals 4py, and plug in 2 for x and negative 3 for y, well, we will see that p equals negative 1/3. X squared equals 4py. We find that p equals negative 1/3. Therefore, the focus is at 0, negative 1/3, and the directrix is y equals the opposite of p, which is y equals positive 1/3. Therefore, the equation, plugging in the p value into 4py, we get is x squared equals negative 4y over 3. 4 times negative 1/3 times y. And here you can see the diagram below in orange. There's, on both of these this slide and the previous one, and throughout the course, whenever I've done examples, I've tried to include similar problems from the text, so you can go back to the textbook and try some additional problems just on your own if you didn't hit pause here. Parabolas have a property that makes them useful in the design of reflectors and transmitters. A particle approaching a parabola on any line parallel to the axis of the parabola is reflected on a line that passes through the focus. You can see that here, it's going through the focus. Okay? As it comes in and hits, it's going to hit the focus of the parabola. This property is used to focus incoming light by a parabolic mirror on a telescope. Alternatively, as you can see in the other diagram, signals emanating from the focus are reflected on lines parallel to the axis. Here, when we have signals coming from the focus, then all the signals are moving parallel, a property used to design radio transmitters and also headlights. You might want to check out exercise 83 in your textbook. There's a solution there for you. An ellipse is the set of points in a plane whose distance from two fixed points, as you see in the diagram here, F1 and F2, have a constant sum, adding the distance of this line segment and this line segment, that we denote 2a. Each of the two fixed points is a focus, plural, this is foci. The equation of an ellipse is simplest if the foci are on the x-axis, plus or minus c, comma 0 are the points, or on the y-axis, 0 plus or minus c. In either case, the center of the ellipse is 0, 0, as you see in this other diagram. If the foci are on the x-axis, as you see in the diagram on the left, the points plus or minus a, 0, I guess I should say a0 and negative a0 are each a vertex. Together they are vertices. And if the foci are on the y-axis, the points 0a and 0 negative a are the vertices. Okay? And here you have a good diagram that kind of shares the point. A short calculation using the definition of the ellipse results in the following equations for an ellipse that we see in the diagram here below and on the next slide. An ellipse centered at the origin with foci at negative c0 and c0 and vertices v1 and at negative a0 and v2 at a0 has the equation x squared over a squared plus y squared over b squared equals 1, where a squared equals b squared plus c. Okay? Now remember, a is the distance from the center to the vertice. C is the distance from the center to the foci, and b is the distance on the minor axis from the center to the equation on the minor axis. Okay? Similarly, an ellipse centered at the origin with the foci on the y-axis, 0 plus or minus c, that you see in the second diagram to the right. Here it's a very similar equation. Notice the conditions are the same, but now it's y squared over a squared plus x squared over b squared. And again, the b is the distance on the minor axis, Okay? In both cases, a is greater than b is greater than 0, and a is greater than c is greater than 0. The length of the long axis is called the major axis, is 2a, and the length of the short axis is called the minor axis and is 2b. Its length is 2b. So let's look at a couple examples. Example 3, graphing ellipses. I've included the x major equation. Remember, this is when x squared is over a squared plus y squared is over b squared equals 1. And that means that the major axis is the x-axis. Okay? So that means it's going to be longer along the x-axis and shorter along the y-axis. Okay? So when we look at this problem, find the vertices, foci, and length of the major and minor axis of x squared over 9 plus y squared over 4 equals 1. What we first have to understand, is this a x-axis or a y-axis, major axis problem? And remember that a is greater than b, so we can see that it's x squared over a plus y squared over b, which is indeed an x major axis. Okay? And so we can see that a is going to be equal to 3, since a squared is 9, and b is going to be equal to 2. Sorry, I lost my train of thought there for a while. Okay? Therefore, a equals 3, b equals 2. The lengths of the major and minor axis, remember, the major is 2a, which is 6, and the length of the minor axis 2b is going to be 2 times 2 is 4. The vertices are at plus or minus a over 0 and lie on the x-axis, as does the foci. The relationship c squared equals a squared minus b squared implies that c squared equals 5, or c equals the square root of 5. Therefore, the foci f1 and f2 are at plus or minus 5, 0, and the graph is shown to your left. Okay, so you can identify all the parts. You need to remember that f are centered at the c points. The b plus or minus b and 0 are the minor axis points, and the a plus or minus a and 0 for the x major are actually the vertices, and you can see that here. So you do have to kind of remember what A, B, and C imply, right? So again, A is the vertices, B are the points on the minor axis, and C is the value, part of the point value of the foci. So another similar equation is to find the equation of an ellipse. A similar example, I should say. Find the equation of the ellipse centered at the origin with its foci on the y-axis. A major axis of length 8, and remember the major axis length is 2a, so we can see that a is 4. And a minor axis of length 4. Again, and the minor axis length is 2b, so we can see that b is 2. So a is 4 and b is 2, okay? So we can use that to calculate C to find where the foci will be, and we already have 4 points. Since it's focused on the y-axis, then the points on that axis are going to be plus 4, like this is on the y-axis, so 0, 4, and 0, negative 4. These are y values, right? The a are the y values in this, since the y is the major focus. And the other points that we have on the ellipse along the minor axis are plus and minus 2, 0. Is that right? We can then find the equation for C, which is a squared minus b squared, and which gives us c equals 2 times the square root of 3. And so the foci are at 0 plus or minus 2 square roots of 3. Okay. Remember, these are x values on the minor length because the major axis is the y-axis. And these are, half of these are the a values or the vertices y values. Okay, so it's a lot to keep in mind there. Am I in the a or the y? And especially when I'm looking at it. Remember, the a is aligned with the major axis. The b is aligned with the minor axis. The distance are 2a or 2b from the points along the major or the minor. And then the c is always the coordinates of the foci, plus or minus c, and then whether it's x or y. So you guys know the drill on this. We're about halfway through the lecture. Not quite. We're a little bit less than halfway. This is a 50-minute lecture. You can either take a break now or go ahead and do the next section on hyperbolas, excuse me, not hyperbole, and do the examples there. I think there are 2 examples for hyperbolas, and then break, or you can take a break now, take a walk, clear your head out, maybe come back tomorrow or come back later and pick up here. I think we're on slide 12. A hyperbola is the set of points in a plane whose distances from 2 fixed points have a constant difference this time, either 2a or negative 2a, and you can see those here. ft, p, this distance, minus this distance equals 2a. As with the ellipses, the 2 fixed points are called the foci. That's f1 and f2 that you see here. We consider the case in which the foci are either on the x-axis, plus or minus c0, or on the y-axis, 0 plus or minus c. If the foci are on the x-axis, the points plus or minus a, 0, so a0 and minus a0, on the hyperbola are called vertices. In this case, the hyperbola has no y-intercepts, but it has the asymptotes y equals plus or minus bx over a, where b squared equals c squared minus a squared. Okay. Similarly, if the foci are on the y-axis, the vertices are 0 plus or minus a. The hyperbola has no x-intercepts, and it has asymptotes at y equals plus or minus ax over b. A short calculation exercise 86 using the definition of hyperbola results in the following equations for the standard hyperbolas. So that leads us to the equations for standard hyperbolas. So let's look at those. So if we have a hyperbola centered at the origin with foci f1 and f2 at plus or minus c0. So here we have an x-axis hyperbola, which is the one on the left here. And so you can see that the parabolas are going left and right when it's focused on the x-axis. Okay. Remember, the vertices are on the equation, on the graph at plus or minus a. So these are going to be x values where it's crossing the x-axis, and has the equation x squared over a squared minus y squared over b squared equals 1. And here we get, and of course we always know that the foci is at the value of c, and here we get b squared is equal to c squared minus a squared. Okay? Similarly, there's also asymptotes. You can see them here, centered at plus or minus bx over a. And so for the y-axis hyperbola, where it's centered on the y-axis, then you see that the equation just changes to y squared over a squared. Okay, and then of course the c and the a for the foci and the vertices are on the y-axis. And here we have ax over b. So this is a big difference here, that the asymptotes are the a value for the when it's focused on the y-axis, and it's the b value, b over a, when it's on the x-axis. So that's a key distinction in these equations. So let's try an example now, just like we've done with each of the other two conics. So graphing hyperbolas, find the equation of the hyperbola centered at the origin with vertices v1 and v2 at plus or minus 4, 0, and foci f1 and f2 focused at plus or minus 6, 0, and to graph the hyperbola. Again, I've just so it's easy for these first examples to remember the formula. And this is the direct formula because we can see that the foci and the vertices are using x values. So we know here our a value is 4, our c value is 6. And so we can use those to figure out our b value, and then we already know where it is. So what are we trying to do? We're trying to graph this, okay? So our equation is going to be x squared over 16 minus y squared. We need to figure out what b squared is. B squared is going to be c squared, which is 36, minus a squared, which is 16, which gives us 20. So we get the square root of 20, which is 2 times the square root of 5. So b squared, 2 times the square root of 5 is b. And so that squared is going to give us 5 times 4, which is 20. Okay? So we get x squared over 16 minus y squared over 20, going through those steps that are outlined here if you want to read them. Our asymptotes for the, when we're on the x-axis, it's bx over a, and so we get plus or minus 5x over 2, because remember this would be 2 times the square root of 5x over 4, so that reduces to plus or minus the square root of 5x over 2, and here you can see the graph there. Okay. And it's even got the asymptote formulas that you can see. Our vertices are at negative 6, 0, and 6, 0. I'm sorry, our foci at negative 6, 0, and 6, 0. Our vertices are at the A value, negative 4, 0, and 4, 0. Okay, and there's our equation of the line. So let's do another example where we figure out the equation given some values. I misspoke. We're actually going to look at a different topic first and then do some more examples. Parabolas, ellipses, and hyperbolas may also be developed in a single unified way called the eccentricity-directrix approach. We let this italic L be a line called the directrix, and F be a point not on L called a focus. So here's the directrix, and F is called the focus. The eccentricity is a real number. Now, don't get this confused with Euler's constant. This is not the constant E that we know from exponential equations. This is just a variable E for eccentricity. The eccentricity is a real number. E is greater than 0. Consider the set C of points P in a plane with the property that the distance PF from the point to the focus equals E multiplied by the perpendicular distance, so perpendicular to the directrix, to that point P. Okay, so PF, the distance from the point to the foci, equals E multiplied by the perpendicular distance from the point to the directrix. Okay, and so we get PF, the distance from the point to the foci, equals E from the distance from the point to the directrix, and again, this is a perpendicular distance. Or PF over PL, the distance to the foci over the distance to the directrix, is equal to this eccentricity constant, which of course is, as we know, is greater than 0. It's a positive number, and that's why we're using, well, these are all distances, so we're using absolute value to indicate distance. Okay, so below you have kind of 3 different examples of different conics. Okay, so we have a parabola here, and for parabolas the eccentricity is 1. In the center we have an ellipse, and notice that for the ellipse the eccentricity is a fractional value between 0 and 1, and for hyperbolas the eccentricity constant is a value greater than 1. So this information we just restate into theorem 12.3 on eccentricity-directrix theorem. Again, in formal language, suppose L is a line, F is a point not on L, and E is a positive real number. Let C be the set of points in a plane, this is just the graph, with the property that PF over PL, the distance values or absolute values, equals E, or eccentricity, where PL is the perpendicular distance from the point P on the graph to L. If E equals 1, then the graph C is a parabola. If E is between 0 and 1, a fractional value, C is an ellipse. And if E is greater than 1, C is a hyperbola. So this is a nice summary of properties of ellipses and hyperbolas, and then it also gives us the calculations for ellipses and hyperbolas using the eccentricity-directrix approach and variables. All of the stuff up here we already know. If it's foci on the x-axis, this is true. Notice that there is no minor axis for hyperbolas, only for ellipses, so this only applies to the hyperbolas. A is on the major axis, B is on the minor axis for ellipsi, C is always the foci, and then of course the directrix is that line D. And then we know that for, as we just saw in the last slides, the eccentricity constant is between 0 and 1 for ellipses and greater than 1 for hyperbolas. But the key part of this slide is these calculations that given any two of the five parameters, A, B, C, D, and E, the other three can be found using these formulas. So C, which is the foci constant, equals A, which is the vertice the major axis vertice, times the eccentricity constant. Again, make sure you realize this is not Euler's constant. And then the directrix constant D is equal to A, the major axis vertice, over the eccentricity. And we already have these for ellipses. It's B squared equals A squared minus C squared. And for hyperbolas, B squared equals C squared minus A squared. So let's try to use this data and specifically these formulas down here. Get these in your notes and make sure you memorize them, and really kind of memorize all of the concepts around these variables and the equations for these different conic sections. So here again, we're looking at an equation of an ellipse. So I reminded you of the equation of an ellipse. And also I added the new formulas that we just saw in the last slide that includes the values of D and E, the directrix and eccentricity constants. We've already been looking at A, B, and C. So now let's look at this problem. Find the equation of the ellipse centered at the origin with foci F1 and F2 at 0 plus or minus 4. So already we see where the major axis is the y-axis. So what changes about this formula, because this is an x-axis ellipse, x major axis ellipse. So remember, the x squared and the y squared values are going to change, okay? And our eccentricity constant E is equal to 1/2. Give the length of the major and minor axes and the location of the vertices and the directrices, and then graph the ellipse. All right. So the foci values are 0 and C. So we know that C is equal to 4. And then we have the eccentricity. So we have a value for C and we have a value for E. So notice that we can calculate the value for A. So A would be equal to C over E. So that's 4 over 1/2. So A equals 8. That's going to give us the length of the major axes, which is 2 times A, or 16. The location of the vertices, which would be 0 plus 8 and 0 minus 8. Okay, and now that we've calculated the value for A, we can calculate the value for D, and we just said that A is equal to 8. So D is going to be 8 over 1/2, or 16. Okay. So we've got A, we've got the length of the major axes points, we did that. I just calculated D, which is A over E. So the directrices are at y equals plus or minus 16. And then the last thing we have to do is figure out B values, so we can figure out the length of the minor axis for an ellipsis. And B squared equals A squared minus C squared for an ellipse. So we get 8 squared minus 4 squared, so 64 minus 16 gives us 48, or 4 times the square root of 3. So the minor axis is 8 square roots of 3, because it's double B, and then the minor axis vertices are at plus or minus 4, square root of 3, and 0. Again, since this is the minor axes, we're no longer dealing with the y values, because this is on the opposite variable line, and so these are x values. And so finally we get the equation y squared over 64, which is y squared over a squared, plus x squared over b squared, which gives us 48 equals 1. And then here you can see the graph of the ellipsis with the two directrix. Anything else I want to point out here? And then all the points. We already had the foci given to us. We added the vertices, major axis vertices, minor axis vertices, and the equation of the line. So you can hit pause if you want to look at this, or you want to read through that solution a little bit better. But the key part is to know these variable calculations and their relationships with each other. So it turns out that conic sections have a natural representation in polar coordinates, provided we use the eccentricity directrix approach that we just used in the last example, and that was given in Theorem 12.3. Furthermore, a single polar equation covers parabolas, ellipses, and hyperbolas. When working in polar equations, the key is to place a focus of the conic section at the origin of the coordinate system. We place the focus at the origin of the coordinate system. Okay, so our focus now is at the origin. All right. And taking a directrix perpendicular to the x-axis through d0, where d is greater than 0. So this is a perpendicular line through the x-axis. So it's perpendicular to x, parallel to y, and the d value is the x value d. So it's d units from the origin. Okay, where d is greater than 0, and the figure you can see is right to the right. We now use the definition that the distance of PF over PL, PF being the distance from a point on the graph to the focus, and PL being the perpendicular distance from the directrix to that point, equals the eccentricity constant, where PR theta is an arbitrary point on the conic section or the graph. Okay, and so here, instead of defining this in x and y, we now have it defined in terms of PR, in terms of r and theta. Okay, and you can see there's our r, and this would be r cosine theta, and this would be r sine theta. All right. Blah, blah, where was I? So okay. So PF, the point from the distance from the point to the foci, is equal to r, and the distance from the perpendicular distance from the L to the directrix is d minus r cosine theta. Okay, so these are really important formulas. PF is r, and PL is d minus r cosine theta. The condition that the distance between the focus and the point divided by the distance between the directrix and the point is equal to the eccentricity constant implies that r equals E times d minus r cosine theta. Okay, and that's just, building this out. Okay, making, setting this up equals E and then substituting these two formulas in there. All right, solving for r, we have r equals E times d over 1 plus E cosine theta. Similar derivation with the directrix at at x equals negative d, where d is greater than 0, results in the equation r equals ed 1 minus E cosine theta. Okay, so on the positive side, we have r equals ed 1 plus E cosine theta, and here we have 1 minus E cosine theta. For horizontal directrices at y equals plus or minus d, a similar argument, exercise 84, leads to the equations. And we saw that there. This would be, while the x value is r cosine theta, the y value is r sine theta. So when we're along the y-axis, this makes sense with our trigonometry knowledge that r is now going to equal ed 1 plus or minus E sine theta. Okay, x-axis, y-axis. Okay, so that's a little confusing because now that I think about it, the directrix, is it's an x equals constant. So x, I think that's the best way to think of it. I was thinking it's a vertical line, so it kind of reminds you of y, but the definition of this line is x equals d. So this is the focus and everything is on the x-axis going through the origin. So this is an x-axis formula to to define the conics in terms of polar coordinates, and this is on the y-axis, or for a horizontal directrix, which would be y equals a constant. So to summarize what we went through in the last slide, and with both, what am I trying to say, horizontal and vertical conic sections that you see in the orange and in the green to the right, we have kind of a summary of the polar equations for these conic sections. Describing the orange graphs to the right, and you can see that with the orange star here, the conic section with a focus at the origin and eccentricity E has a polar equation, R equals ED over 1 plus E cosine theta, and or R equals ED 1 minus E cosine theta. If we have the kind of more vertical origin, horizontal origin, where they're going up or down, this is the green graphs, and I put the stars over here so you can connect them. Here we have R equals ED 1 plus E sine theta, or ED 1 minus E sine theta, okay? I wish I had put that other graph on there, but you can go back to the last slide and see that. And remember, if E is between 0 and 1, we have an ellipse. If E equals 1, it's a parabola. And if E is greater than 1, it's a hyperbola. And the curves are defined over any interval in theta of length 2 pi, right? 0 to 2 pi. Okay? So let's try our last example for, oh no, we have 2 examples. My bad. Let's try our last 2 examples for this course. So let's figure out now how to graph these curves using polar coordinates. I put a general form of the equation, just one of them, just so we have it to kind of do some calculations from the last theorem, okay? So when we're trying to graph the first one, notice that in the denominator, we're trying to create this look of 1 plus E cosine theta, and yet we have 2 plus 3 cosine theta. So we need to get this constant changed to a 1, and then the multiplier or coefficient in front of cosine theta will be equal to the eccentricity constant. So in order to turn 2 into a 1, we multiply by its reciprocal, or 1/2. So we get, if we multiply the denominator by 1/2, we get 1 plus 3/2 cosine theta, which makes E equal 3/2. But if we're going to multiply the denominator by 1/2, we have to do the numerator as well. And that, in effect, gives us an equivalent equation for R, which is 4 over 1 plus 3/2 cosine theta. Now we have this in standard form. It allows us to identify E equals 3/2. Therefore, the equation, because E is greater than 1, we have a hyperbola. Okay? The directrices are vertical because cosine theta is equal, is in the equation, and that's easy to remember because, remember, in trigonometry, cosine was the x value. So that can kind of help us think about the directrix being vertical, which are x equals a constant. Okay? And knowing that the numerator is ED, and we figured out what E is, so we get, I just went blank there, D is going to be equal to ED equals 4, that's the numerator, so D is going to be 4 over E, or 8/5, 8/3, excuse me, 4 divided by 3/2, let me slow down here, equals 8/3. And so one directrix is 8/3. Letting theta equal 0 and theta equal pi, because those are both on the x-axis, the polar coordinates of the vertices are 8/5, 0, and -8 pi. Now this is a little bit more challenging to kind of figure out, you know, conceptually, and part of that is because we're really generally more familiar with Cartesian systems. And so while this first vertex we see because of it being at the 0 point, and it kind of looks like a XY coordinate, and in truth it is a Cartesian coordinate as well. It's interesting that it maps out in both. But the other vertex, 8, 0, it's hard to kind of reconcile that conceptually with the polar coordinates, which are -8 and pi. Okay. Equivalently, the vertices, okay, we just said that about the in Cartesian coordinates. The center of the hyperbola is between the vertices, therefore it's Cartesian coordinates. It's the difference between 8 and 8/5 would be 24/5, you know, halfway between them. The distance between the focus at 0, 0 and the nearest vertex is 8/5. Therefore, the other focus is 8/5 units to the right of the vertex, 8, 0. And there you see it there. So the Cartesian coordinates of the foci are 48/5, 48/5, 0, and 0, 0, right? Because the directrices are symmetric around about the center, and the left directrix is 8/3, the right directrix is x equals 104/15, which is approximately 6.9. Okay? So they have to be an equidistance from the center, which is at 24/5, and this one's 8/3, and so we do the same. Find the distance between those two, and then add it to the 24/5, and that's how you get the 104/15, right? And you can even see that because the common denominator between fifths and thirds is 15. Okay, let me see if there's anything else I want to tell you here. And of course, since we're using polar coordinates, we're going to graph it from 0 to 2 pi. All right. These are a bit confusing, but as we've seen from the introduction to this section, these do have a lot of applications in the real world. So let's look at part B now. Down. Okay. Let me see if there's anything else there. The vertex corresponds to theta equals pi/2 and has a polar coordinates 1 pi/2 or Cartesian coordinates 0, 1. Setting theta equals 0 and theta equals pi, the parabola crosses the x-axis at 2, 0 and 2 pi in polar coordinates, or plus or minus 2, 0 in Cartesian coordinates. As theta increases from -pi/2 to pi/2, the right branch of the parabola is generated, and as theta increases from pi/2 to 3 pi/2, the left branch of the parabola is generated. These are really, again, I think they're kind of logically or intuitively difficult to follow because we've spent so much of our lives focused on the Cartesian system and kind of translating a polar coordinate grid onto a Cartesian system. It doesn't quite make the intuitive sense that we're used to with graphs really explaining what's happening with an image. Okay, I'm not going to spend a lot of time. There probably won't be any, there might be test questions on this. There certainly will be test questions on the polar coordinates, but this will not be on the final. Looking at the example 8, I've decided not to go through that example. You can look at it in the text if you'd like to, but it's really more of an interpretive thing using a graphic utility, and I don't think it has any kind of analytical value to you in this course. Perhaps later in your career, you know, it might be of some value depending upon what field that you're working in. But basically, this is the end of Calculus 2, and we've covered all the lectures, etc. And that's all, folks. So good luck on the last test and good luck on the final exam, and reach out if you need anything.